next speaker, who is Andrei Lavrenov from St. Petersburg State University and the Euler Institute, and he will give a talk on Morava motifs of projective quadrics. Please.
Thank you very much. Well, I'm very grateful to the organizers for the opportunity to speak here, and I will speak on my joint results with Viktor Petrov and Pavel Sechin and Nikita Semenov on well, Morava K-theories. So well, I will discuss motifs of projective quadrics. So we'll consider just Q, which is well, something in projective space. Q is quadratic form, and D is a dimension. And but well, when I say motifs, I mean generalized motifs, well, pure motifs, but where in Grothendieck's definition, instead of Chow theory, we will use some other oriented cohomology theories. So objects are, so well, in the category of correspondences, maybe, but we take the projective smooth varieties over a field, and as well, maps, we take usual A d max x times y for y reducible, but here A is not the, I mean, not the Chow theory or something for Chow out, but can be any oriented homology theory in the sense of Levin-Morel. And well, maybe one of the first who considered other theories than Chow, well, was Ivan Panin, who took K0, Grothendieck's K0 as A, and well, he computed K-theory of projective homogeneous varieties, and well, in fact, also the K0 motifs. So, for example, for the case of quadrics, he proved that its K0 motif has well, lots of summands. In fact, it has at least, I think, D+1 summands. It is the dimension of the quadric. However, the Chow motif, generally speaking, can be indecomposable. Well, what we looked for as for some theories A, well, in between these two situations, so where the motif is decomposable maybe, but not that much as the K0 motif. Yes, and well, I would like to say that Levin and Morel constructed universal-oriented cohomology theory, oriented cobordism, and oriented cobordism itself, well, is not an interesting example because, as Bishop and Yagita proved, omega motifs well, and well, have the same motivic decomposition as Chow motifs. And since so in particular for quadric, the motif can be decomposable, and obviously since omega is universal, if we have some decomposition, well, in terms of omega motifs, then we will have such a decomposition in terms of other theories. But the indecomposable omega summits can become decomposable. Or maybe instead of omega, we can speak about Chow. So like the Chow decomposition is, I don't know, the coarsest, maybe the road. And then for other theories, the motif becomes more split. And so, well, omega itself is not that interesting, but obviously it's a source of examples, because in fact, we can just take any formal group law over any ring, and we can consider a theory with this prescribed formal group law. So I will maybe briefly recall that each oriented cohomology theory is endowed with a formal group law. Well, in fact, it's endowed with characteristic classes for line bundles or any vector bundles, in fact. And well, if we try to compute a characteristic class of the tensor product of line bundles, then we will have some, well, some series Chern classes of N and M. So here F is just a series over the ring of A over a point. And well, obviously we have some kind of commutativity and associativity, because this holds for this line bundles. So the series with these properties are called formal group laws. And for omega, we have well, the universal formal group law, which means that omega point is the Lazard ring, and F omega is some formal group law over L. And this ring has a property that, well, formal group laws over ring R are in the one-to-one correspondence with, well, just maps from N to R. Meaning that under this map, the universal formal group law goes to some other formal group law, and we can get any formal group law in this well, way. And well, taking some formal group law, we can take a map which classifies this law, and over this map we can make a product, and this also will be an oriented cohomology theory, because, well, we can tensor the axioms. So the theories which are obtained by this procedure, I will call them free theories. They share many nice properties of algebraic cobordism, but the one which will be most important for what I will tell is the recent theorem of Gile and Wischek, where they prove that for these theories, the Ross-Nilpotens principle holds. I will Nilpotens principle. So as for usual Chow motifs, we can well consider, so well, we should take X to be a projective homogeneous variety with a semi-simple group, and we should well take a free theory. In fact, they do it in larger generality, and they construct some examples of theories which are not free, but for which their theorem holds. But they also provide many examples of theories for well, which they cannot prove anything. So in fact, it's rather restricting. And then for any field extension, if we consider the restriction homomorphism for, well, a, so let me write like this, an endomorphism ring of X in the category of correspondences to the endomorphism ring of X times L over K. Then the kernel of this is some restriction homomorphism, and the kernel consists of nilpotent elements. Nilpotent, well, obviously, I mean with respect to the composition of correspondences. Well, now I will tell you about our particular choice of free theories, namely about Morava K-theories. So I will explain you how well we can define them. So the usual procedure is the following. One passes from omega to BP theory. And this is like when we pass from integers to integers localized at prime ideal P. Then, well, due to the theorem of Cartier, any formal group law over ZP algebra is isomorphic to a P-typical one. Well, I will not recall the definition, but the idea is that when we work over ZP algebras, we can restrict ourselves only by P-typical laws, and instead of universal formal group law, it's more natural to consider universal P-typical formal group law, which is over some ring usually denoted by V, which is isomorphic to ZP with infinite number of polynomial variables of degrees of these degrees. And this isomorphism, in fact, can be chosen, well, in different ways, but it can be also chosen in such a way, well, in one very, very nice particular way, which is called Winkel's choice of generators. Winkel's choice of generators. I will then say what it means for Morava. Yes, and then BP is just, well, the theory which corresponds to this universal formal group law. And if we consider natural maps from V to FP V n plus minus 1 for some fixed n, so we should fix P here, and we should fix some n, consider such a map. Then, well, this universal formal group law will give a certain formal group law over this ring, and the corresponding theory called Morava K-theory. So I would like to give a few remarks on different possible definitions of this thing. So first of all, well, in this talk I will only work modulo P, but in fact one can, so maybe remarks. So one can consider, well, like ZP integral versions, so, which are also called Morava K-theories, and they are useful for some reasons, but for motivic decompositions of projective homogeneous varieties, well, at least for simple groups or the inner forms of split semi-simple groups, then, well, the motivic decompositions, so let be A, motivic decompositions with respect to this integral Morava and with respect to Morava modulo P are the same. A and okay. And in fact, just the proof, well, just the proof from the paper of Chernousov and Merkuriev works for Morava verbatim. So that's because, well, we already have local coefficients. It's not integers, it's integers localized at P. And we can work modulo P. And also, I would like to mention that, well, we can consider this formal group law of Morava K-theory or rational numbers, in fact. And then, as any formal group law over Q algebra, it will be isomorphic to the additive one, to just x plus y. And the isomorph, that means that there just exists a series such that this identity holds. So this is the our formal group law, and this is the additive formal group law. And our choice of Hasse-Weinpitz generators guarantees that, well, this form has a very simple form. I will write it down. So here we have Vn to some power, and here we have P and K. And the power, well, it's the only possible, but it is something like that. So if, for example, we just put 1 instead of Vn, then formula is very simple. So, and in fact, we can, well, take this as a definition. So just define Fn of xy as a, well, here L minus 1 means composition inverse, and prove that it is, in fact, doesn't have denominators, and then take it modulo P and define Morava K-theory using this concrete formal group law. And also, I would like to mention that, for example, using this description, one can prove directly, but that, well, I will denote by, I will denote this by this, and I will denote the P, or maybe, and well, I take the sum n times, I will denote it just like that. So it's not hard to show that the f of x is in fact well, x and here also Vn modulo p. So, well, in particular, it's well known that, well, in fact, for any series over quadratic integers with which starts from et and which has this property that one can construct a formal group law over quadratic integers, and it's a construction of Lubin and Tate. And then if you take it modulo p, you will get, well, again, our formal group law of Morava K-theory. So now I will speak about Morava motives. Maybe I also should mention that, well, so first, if we start from a split quadric, then it's cellular, and well, its motive decomposes, well, as a sum of, write it like that. I will write bar everywhere. Decomposes as a sum of twisted motives of a point, which I will call Tate motives. So it's well known for Chow theory, for example. Then we could use this Nikita result to well, obtain that that's true for Cabourdes motives, and by universality, it's in fact true for isomorphism, in particular for Morava motives. Well, there are some funny theories with decomposable motive of a point, but for Morava this doesn't happen. We have a local endomorphism ring of a point. If we have, so what are motives? They are just some projectors in the morphism ring. So if we take some quadric which is not necessarily split, and when we do this restriction map to the splitting field, then well, it's the image of the idempotent is still an idempotent. And if we have like some full system of idempotents, we still get full system of idempotents. But obviously they can be this well, here we may have some undecomposable summand, and here it decomposes as a sum of these twisted motives of a point, because, well, this is the decomposition into indecomposables. And well, the number of these Tate motives is called the rank of the projector. So the rank of pi is a number of Tates in the decomposition of pi. Well, it's as for Chow theory, I will draw pictures. For example, if we have, I don't know, 4-dimensional quadric, then we will write as usual something like that, meaning that these are motives of a point, but maybe shifted. And here we put, well, those which are not shifted, shifted by 0, shifted by 1, by 2, and so on. And well, if before splitting our quadric, I have some summand which splits into these two Tate motifs, we well, can connect them or maybe join some in some way. Well, obviously, this picture is not maybe very suggestive for Morava K-theory as is, because, well, for example, if we take p equal to 2 and n equal to 2, then we'll see that motif of a point twisted by 3 is isomorphic to the motif of a point. And in fact, always motif of a point twisted by Vn minus 1 is isomorphic to the motif of a point. That just because this Vn and Vn minus 1 give this isomorphism. And maybe instead of this picture, here we should write something like that, but since it's very strange, well, we will not do it. So I mean that this is, well, 0 and 3, this is 1 and 4, and this is 2. And maybe when I will explain the material decomposition of generic quadric, this will be, well, it will be maybe more or less clear that this point of view is still okay. So now I would like just to state the theorem. So let Q be a generic quadric. In fact, one can take a sort generic, but doesn't matter. And well, let P be equal to 2, because for odd P, since it's a quadric, motif decomposes as for Chow tensor Q. So it's not interesting. And also, let's take n greater or equal to 2, because for n equal 1, motif decomposes as K0 modulo 2 motif. And so then, well, if dimension of the quadric is less or equal than 2n minus 2, Kn motif is indecomposable. And if dimension is greater than 2n minus 1, then Kn motif contains an indecomposable summand of rank 2n or 2n minus 1 for the even, respectively odd. And all other summands are Tate summands. But I don't have time, I don't have place to write it somewhere. Maybe I will try. And all other summands are Tates. So we can try to draw a picture, for example, for even dimensional quadrics. So if we take K2, so then this is the decomposition. And and these are just date summations. And if we take K3, then we have something like that. If we take K4, then we have something like that. And in a certain sense, in the limit, when it goes to infinity, we just get at some step decomposable summand as we have for Chow. So maybe another way to visualize that is that we have this part, which generally speaking is indecomposable, and it exactly has the same structure. So we don't have isomorphic date summands here, except these two. So it has, in a sense, the same structure as for Chow. So this is for n equal to 3. And these are some date summands, but in this, well, we cannot confuse them maybe with this one. So I think this picture is still okay. So now I would like to speak about the proof of this result. So the proof consists of two parts. First is just to find the required amount of date summands. Well, and the second one is to prove that the motive has an indecomposable summand of big rank. A big indecomposable summand. And in fact, both parts, they just investigate some structures on Morava ring of a split quadrant. Well, this is, so it's well known that this is a free module over Kn of point. And as a base, well, we can take, well, Li, which are classes of projective subspaces into this split quadric. Is is like this. So, and well, I mean, push forwards of the identities of Kns of these rings under the push forward, and by also by H, I will denote this characteristic class of O1 on Q, and then this i's and powers of H form a base of this ring. As for Chow, this works for any theory. So in fact, what we will need for the first part is just the Euler characteristic, in a sense. And by this I mean, well, if I denote by chi the structure map to the point, then let k sub kn denote just a push forward. So this I will call Morava Euler characteristic. Or maybe I don't know a better name for it. And well, it's not hard to describe it explicitly. I can just tell you the answer. So for Li, it's in fact very well known. It's called Mishenka formula. But for Hi, the formula is the following. It's Vn for I equal to t plus 1 to n and 0 elsewhere. So, well, I recall that here everything is modulo 2. And in fact, this formula is just that formula for 2 of t. Yes. And then I think it's more or less clear how to find this required amount of Tate summons. Well, but I will recall that since we have Grothendieck's principle, okay, so we can, it implies, okay, let me first write again this map. So this implies in particular that if we have some, let the image be denoted by R, and Grothendieck's principle implies that if we have something which is from this image and idempotent, then in fact it comes from the idempotent here. Then phi has a preimage that is idempotent. So in fact, we can just we don't have to work with this ring. We can work with its image here and look for idempotence here. And well, since H is rational, because it was of the bar of 1, and it comes from of Q of 1. By rational, I mean those who lie in this image. Rational, which means it lies in R. Then, if we construct some idempotence using only H, then this will give us rational idempotence, and by Grothendieck's principle, some materic summons of Q. And looking at this formula, in fact, it's not hard to see that just let this be d prime. And if we consider H I times H d prime minus I, and here Vn minus 1, then this is the system of orthogonal projectors, and we have exactly as many as we want. And well, I mean, I don't know, just using the usual formula that this is a by Kn AD. Since Q prime is similar, we also have QNet formula for it, and we can write formula like that. And well, now it's clear that these are orthogonal idempotencies. And for the second part of the proof, we need another structure. Namely, we need the structure of homogel over Kn of special orthogonal group. So since, well, Q prime is write as so d plus 2 modular certain parabolic, then and so d plus 2x on it, then well, when we can consider Morava K-theory of this group variety, or theory, and taking pullback of this action, we will get coaction on Kn of K. And due to the theorem of Viktor Petrov and Nikita Semenov, well, if we have a motivic decomposition of a generic quadric, so if we have, say, A be a free theory and Q generic quadric, in fact, so generic, or maybe just generic generic GPP, I don't know. Generic projective homogeneous variety. Then yeah, and moreover, we have a motif of X decomposes. It's a direct sum. Then, well, its realization. Well, I mean, just we can take a of this Ni, which it just maps to the point. Maybe twisted. So, okay, we should do it not like that. We should first take an I over splitting field. And then take their realizations, and then A of X I will decompose as the sum of the realization, obviously, but this is the sum of Checker modules. Checker modules. Okay, let me maybe say it again. So say A is a free theory and say X is a well, a generic projective homogeneous variety. I mean, like twisted by means of generic torsor, and assume that it decomposes, its motive decomposes, then its realization decomposes, in fact, as well as a sum of AFG comodules. And they prove more. In fact, if it's not generic, then you should, instead of AFG, take some quotient. By A of E, if we twist by means of this E, and then that will be the sum of A of this quotient, comodules over this quotient. But well, for generic torsor, this is trivial in a sense. So quotient in terms of augmented coalgebra, so for if it's A of a point, then this will be just A of G. So, but what does it mean if we just use it as an application? Well, if we just want to have some applications of this thing, is that if we can determine the structure of Kn of Q as Kn of Sm comodule and prove that it has an indecomposable comodule of big rank, then we will have the same for motives. Then this will imply that the motive has an indecomposable summand of big rank. And since we already know that having a required amount of Tate summands, then this motivic summand should be of exactly that rank that we expect. And in fact, we can say more. Well, we can do it a little bit differently, I think. That obviously, if we have some generic quadric of dimension d, then we can split it into generic ways. So we can take some field extension such that it becomes isotropic, but it has with index, and an isotropic kernel is again generic of dimension d minus tau. And on motives, this gives well the well-known decomposition, obviously. This let it be Q prime. So, in fact, this means that if we prove that, well, this quadric has an indecomposable summand of rank 2n or 2n minus 1, depending on the parity, then this one also should. Yes, because this one also should. So in this computation of the coaction on, we only need to consider the cases when m is less or equal to 2n plus 1, I guess. And up to this range, we can just, in fact, compute this thing. This will be isomorphic to the Chow. Not very interesting. And the coaction also will be the same as in the case of Chow. for m less of 2n plus 1 and for m equal to 2n plus 1, the same. Correction is different, but it is easy to compute it. This, in fact, shows that in this range, well, Chow motive is indecomposable, but a Morava motive decomposes into parts of rank 1 and of rank 2 n minus 1. And we can also observe that this exactly corresponds, so this d equal to 2n minus 1 exactly corresponds to the case where we have just one projector, 1 times 1. So we had there something like this, and here it is 0. So this is exactly 1/8, and the rest is decomposable. And at the end, I would like also to mention that we can get more in this, in fact, the computation of the Morava of special orthogonal group. In fact, we can prove that this thing is the same up to n plus 1, non-canonically as algebra, but the correction is different. And after this range, Morava happens to stabilize. For m starting from 2n plus 1 plus 1. So that is the answer. So it's the same as Chow modulo 2 up to this range as algebra, and then it stabilizes. So something interesting happens between these two ranges, because correction begins to change. And here, well, we have the isomorphism of algebras. Correction also stabilizes. But we can't currently compute it. Well, we can compute it for the second Morava because it's very small. Because I mean, this range is very small. It stabilizes very early. And I will write here maybe as an example the coaction. So Kn of SOM is just F2 plus minus 1 E1 E3 modular E1 to the power 4 E3 to the power 2 for m greater than 5, I guess. And but these are not primitive. This is this has the following. So here we should add Vn, I guess. But this is explained by the formal group law. This is clear. And here we have something strange, which we can compute, but which we don't quite understand. plus two symmetric summands. E1 E1 square and one more like that. Okay. Just leave it like that. So this maybe that's all that I wanted to say today. Thank you very much.
Yeah, thank you. Thank you for a wonderful talk. Is there any question? Any question? Please use either chat or just switch on your mic. And is there any question? Oh, I have a question. So what's happening for the spin groups? Were you able to compute some?
Yes, but for
coaction?
spins, it's simple if you have special orthogonal, because I mean, if you have this sequence, yes, and for the same for spin, but just with another torus. So for spin, you will just have the quotient of this by something, and you can explicitly say that you should, I mean, just kill E1.
And do you have an understanding of this delta of E3 in this case for the spin groups?
Yes, but I mean, the understanding, I mean that we will have this formula because E1 will go to 0, but that's not quite a formal group law, so I don't know what does it mean. Not philosophically.
Okay, are there more questions? So if not, then let's thank a speaker. Thank you very much. And we resume in a week. Thank you.
Okay, thank you very much.